everyone, I'm Norman Wellberger, and today we are going to be talking about arithmetic with Monopoly money. So we want to explain why this new idea of open numbers, which is an alternative to the usual Hindu Arabic closed number form, is a useful a useful option for educators to think about in terms of explaining arithmetic to young people. And it has very natural connections with the usage of money, and I want to illustrate that. And I also want to talk a little bit about the idea of playing games in the sort of educational context. So Monopoly, of course, a very famous game introduced in 1935 by the company Parker Brothers, created by Lizzie McGee and Charles Darrow. And we have a board like this, and you go around these squares. Each of the squares represents a property, and you can buy the property if nobody already has it. And then if other people land on your property, you can get rent from them. And sort of at the end of the day, people can create some exchanges and create little monopolies and hopefully bankrupt other people and get most of the money themselves. Okay, so that's the basic idea. And it's a very popular game, and I think it's a really good thing for educators to think about in terms of introducing into schools. I'm thinking about having a classroom where the desks are organized into, say, tables of 4, and groups of 4 or 5 kids are around each table, and they're each playing a game of Monopoly. And I think this is a great thing to do. In fact, even in math class. So it's not unreasonable that young people get a chance to actually play and to practice their arithmetical skills in this somewhat fun context. That would make mathematics classes a lot more entertaining and something to look forward to. So I think that's a really a good idea, and I think we're going to talk a little bit about the advantages of that today. Now, behind all of this is a monetary system. So Monopoly has money, and okay, I have a Monopoly set around. So here's like $1, and here are $10, and here are $100 in this Monopoly money. Actually, there are other values as well, but for us, we are going to just consider the ones, the tens, and the hundreds. That's really all what we need to do for the purposes of today's talk. And because naturally these are connected with our Hindu-Arabic system, our way of representing money. So that's a great thing. So we're going to use these things physically to try to get young people to understand arithmetic and to also illustrate the power of open numbers. So what are the benefits for young people to play Monopoly? Well, it strengthens counting. Because first of all, they have to roll dice, and then they have to move this marker around the board, and so they have to count, wherever they are. We have to count 7 more, or 11 more, or 12 more, or whatever it is. So they're counting around as they go. So actually, when they roll the dice, there are 2 dice, and so what they have to do is they have to add up the 2 numbers on the dice. That's the total number of squares they're supposed to move. So 6 and 2, they have to move 8. So it strengthens, in a small way, the ability to add numbers, small numbers. And it also teaches them about money, about real estate, and the idea of renting, getting some rent, and buying and selling. Also taxes, because there are all these other cards that sometimes invoke various financial events. So it's quite a good game to sort of connect a little bit with the real world. Of course, reading is an important aspect because they have to read the names of properties, and ultimately they have to read the names of things on cards and so on. So that's an important aspect, and admittedly that might only be suitable, or that aspect of the game might be more suitable for older kids once they've learned to read. But if you have younger kids, well, you can just dispense with the cards or make them some simpler thing. Buying and selling and trading, they develop some money sense. The relative worths of things. Are these 2 properties sort of equal to those 3 properties, in terms of an exchange and so on? So they have to get some kind of connection with the values and the real estate. And of course, it also promotes negotiation, because at the higher levels of the game, they have to trade and make good deals, and they have to get along, perhaps, at some level with the other people in the game to make favorable deals. So there's lots of really So perhaps indirect benefits. It's not ticking directly boxes in a mathematics curriculum, but I think it's supporting general educational things which are important. So I think it's not a waste of time for young people to spend time in class. Something they can then look forward to. Today is our Monopoly day. It's fun. Let's go to math class. It's exciting. I'm gonna bankrupt you today, etc. Okay. So I think that's a really fun thing to think about adding to the educational environment for young people. Now, apart from the game itself, just having some Monopoly money around is a useful tool to teach people arithmetic, because we can tangibly create something physical that represents these abstract numbers that we write down on the page. It's very powerful. And it's especially useful to encourage young people to understand open numbers in this novel approach to some aspects of arithmetic that I'm promoting. So we're going to stick with $1, $10, and $100 today. If you have some $1,000 bills, that might be useful as well, but I don't think most Monopoly sets have such. So let's give an example. So we have Anne and Bob, and Anne has some money, and Bob has some money. Anne has 3 $100 bills. 1, 2, 3. She's got 7 of these 10s. 1, 2, 3, 4, 5, 6, and 7. Okay, there's those 10s. And how many ones? She's got 5 ones. 1, 2, 3, 4, 5. Okay, I think that's right. Okay, so this pile of money represents Anne's money. 3 $100 bills, they're in there. 5 $1 bills there, and 7 $10 bills. Okay, so that's Anne's money. And then Bob has 4 hundreds. Okay, 1, 2, 3, 4. 2 10s, 1, not so easy to do this with 2 hands. 1, 2, and just 1 $1 bill. All right, okay. So here is Bob's money. A $1 bill, 2 10s, and 4 hundreds. Okay, so that's Bob, and here is Anne. Okay, and now we ask the question, how much do they have altogether? Now, this is a very interesting situation here, because we can solve this problem even if we're just a kindergarten student with almost no understanding of arithmetic, in a very simple and direct way. And I'm going to show you. We just put them together, and I'm going to put them together in a slightly organized way so that the blue ones are all together and the white ones are all together and the yellow ones are all together. Okay, so I've just combined them physically. Okay, what do we see now? Well, there's the total amount of money that they have. So this is, in some sense, a real answer to the question. And it's interesting because it's circumvented any need for an arithmetical abstract system. Okay, we don't even need to have names for the numbers. We don't need to have a way of writing them down. We don't need to have any skill in sort of abstract operations. We just perform this very physical, bringing them together. So that's a physical union of the bills. So we can verify in this case that the two answers are directly corresponding. The physical union of the bills, the very naive kindergarten approach of adding things, corresponds with this more sophisticated arithmetical process involving knowing about numbers and rules for arithmetic and so on. And now let's have a look at a slightly more sophisticated version of the same problem. Now Kara has 2 hundreds, 5 10s, and 7 1s, while Dave has 3 hundreds, 9 10s, and 6 1s. Okay, so now I have their monies here. So here is Kara with 7 1s, 5 10s, and 2 hundreds. And over here is Dave's money with 6 1s, 9 10s altogether there, and 3 hundreds. Okay, So same kind of thing, except the numbers are just a little bit bigger. But how much do they have all together? So there they are, now they're together. Okay, so that's the process of adding the numbers. Okay, we could then organize them so that they're together, but it's not really necessary. That is the total there. That's an answer to the question. But another more sophisticated answer is this one here, where we take the number representing Cara's amount, which is 257, and we take Dave's number, which is 396, and we add them with open numbers. Okay, now that's the mathematical analog of what I've just done physically. We add the 7 ones and the 6 ones. Right? So altogether, if we counted the ones, there would be 7 plus 6, there'd be 13 ones in this pile. And the total number of tens, well, there'd be 5 plus 9, so the total number of tens, if we organize them, there'd be 14 of them. And the total number of hundreds, there'd be 5 of them. Okay. So this computation here, which is at the level of open numbers, it's an open number representation of what we're doing physically. Okay, it just exactly corresponds to the physical putting them together. Now, if we want to go further and get a traditional answer, then we should convert this open number using cascading. So that's sort of a next level where we would take the 13, the 14, and the 5 and put them together in this cascading staircase fashion, with the 3 here representing the ones, the 1 and the 4 in the tens position, and the 1 and the 5 in the hundreds position. And then when we add them, we get 3 ones, a total of 5 tens, and 6 hundreds. So we get a Hindu-Arabic number, which is equivalent to our open number, 653. Now, I want to compare this with a more traditional calculation. So traditionally, what people would do in order to determine the sum would be to write 257, Cara's number, and 396, Dave's number, one on top of each other, aligned in the right way. And then we would write down the totals in each column, but in a kind of a clever way. So the 7 plus 6 is 13, and we write the 3 there, and then the 1 ends up becoming a little blob up at the top of the next column. And then when we move over to that next tens column, we have to add that little blob to the 5 and 9 for a total of 15. Again, we write down the 5 and the other 1 in the 15. It comes up here as a little addition to the hundreds column, and then we add up all of those to get 6. So we're still really writing 13 and 14 and 5, but in a kind of an indirect way. And it's a little bit different, right? Because the 13 is kind of appearing here, and the 14 and this 1 have been combined to give a 15, which is appearing here. So this kind of traditional computation is, I think, awkward. Okay? It's maybe efficient if you're very good at it, but if you're not very good at it, there's all kinds of errors that can creep into this kind of thing. And especially if the numbers are bigger or there are more of them, then the possibilities for errors really mount up very significantly. So it's actually quite questionable whether this is the right or the best way of thinking about teaching young people to add numbers. Okay? I'm proposing that it's not the best way, that it's better to think about this procedure that starts with this open number calculation, which is just a direct analog of the physical putting togethers of the physical monies, and then having a second stage of cascading those, arranging them so that we can add them up in the right ways to essentially deal with the carries at this stage. So we're separating the additions from the carries. Okay? So this is an alternative, and I think it's an alternative that needs to be taken very seriously by educators of young people. So this new calculating with open numbers technology has some serious advantages. First is that all of the working is shown very directly. So the errors, if there are any, hopefully there aren't, but if there are errors, they can be found quicker and they can be corrected. The addition and the carrying operations are more clearly separated. They're not interwoven as they are in the traditional method. We are separating the additions. That's what we do first, and once we have the additions all out of the way, then we turn to the carrying problem. That's, I think, conceptually simpler, even if maybe it appears to require a little bit more work because we have now sort of a stage 1 and a stage 2 process. We'll see that it works better with horizontal and vertical sums. So it gives us more flexibility in the form of the questions that we can address and the actual way we can physically use the page to make the calculations. And I'm going to introduce the idea that there's something called big end approach and little end approach that sort of has to do with whether we're thinking about a number as being principally starting from the little end, which is the ones and then the tens and then the hundreds and so on, or starting from the big end, which is like the biggest numerals, like the thousands or the hundreds, and then working our way down to the ones. Okay? So if you have some number, there's these two kind of approaches. You could go this way or you could go this way, and the open number approach allows you more flexibility to appreciate both of those approaches. That's quite an advantage. So I want to explain a little bit more these 2 points, which are less obvious. So I want to illustrate that by having a look at this concrete problem. We have to sum 417 plus 846 plus 709 plus 925. And let's first start with an open number approach, where I'm going to sort of proceed with the little end orientation, which is more or less what I've been doing up till now. That means that we're going to think about all these lanes as separate, but we're going to think about the ones lane as what we work with first, and then the tens, and then the hundreds, and so on. So starting from the little ones and working our way up. So what we can do is look at the ones. There's ones at the rightmost digit here, and so we're going to add them up. And we do that mentally in our heads because we are well trained in doing that. Okay, so 7 plus 6 is 13, plus 9 is 22, plus 5 is 27. So I'm going to write down 27. I'm going to put it over here on the right-hand side. That's going to be our ones column. And I'm going to put a comma here, and over here now I'm going to put the tens. So now I go back to the numbers, and I'm going to collect the tens as I go along. 1 plus 4 is 5. Plus 0 is 5, plus 2 is 7. Okay, so that's the total number of tens. Now I put a comma, and now I'm going to count the number of hundreds. 4 plus 8 is 12, plus 7 is 19, plus 9 is 28. So I get the open number, 28, comma 7, comma 27. Now, how would a big end procedure work? Well, it's the same kind of thing, but we're just going to start with the biggest digits first, namely in this case the hundreds. Hundreds, 4 plus 8 plus 7 plus 9, 4 plus 8 is 12, plus 7 is 19, plus 9 is 28. Then the tens, 1 plus 4 is 5, plus 0 is 5, plus 2 is 7. And the 1, 7 plus 6 is 13, plus 9 is 22, plus 5 is 27. Of course, we get the same thing, but we're proceeding this way as opposed to this way. And I hope you can appreciate that there might be situations where this is more natural or useful, but there might also be situations where this is more natural or useful. It doesn't matter. You're going to get the same answer, and it's because the lanes are all separate. So it doesn't matter whether you start organizing or recording things from this side or from this side. There's a fundamental symmetry to the situation. The mathematics is not sort of directing you in one way or the other. Okay, so now let's take this answer and convert it into an actual Hindu-Arabic number by some cascading. So we'll put the 27 here, establishing the ones column and the tens column. And then the 7 represents 7 tens. And then the 28 represents 28 hundreds. That's sort of separate. So our cascading is like this. We have a staircase pattern like this, and then we can form the sum, which is 7 9, 8, and 2. And that's our answer. Now, I want to compare that with how a classical student would do this. A classical student would find it necessary to first rewrite the question so that the numbers are vertically aligned. The first step would be to rewrite it as 417, 846, 709, and 925, where we've organized so that the ones are all aligned, and so are the tens, and so are all the hundreds. And then they would necessarily start with the little end, with the ones, and add them up, much as we've done. 7 plus 6 is 13 plus 9 is 22 plus 5 is 27. So now there's a 27. So we're going to put the 7 here, and we're going to add the 2 up there somewhere. We have to make a small little 2. Okay, now that's added to the list. So now we start with the top, perhaps. 2 plus 1 is 3, plus 4 is 7, plus 2 is 9. Okay, so there's a 9. In this case, there's no additional carry. And finally, 4 plus 8 is 12, plus 7 is 19, plus 9 is 28. So this is 8. And then actually, strictly speaking, we should put a 2 up there to be consistent in the next column, which of course doesn't have anything in it in this case, but it could have. And then we have to add up everything in that column, and of course that's just going to be the 2 coming down there. So I'd like you to think about the differences between these two approaches, and think about what the differences might look like if there were not just 4 numbers here that we had to add, but maybe 10 or 20 of them. With the open number approach, we do not have to rewrite them vertically, because it doesn't matter for us. We're keeping the lanes separate, so it's not so easy for us to get confused. Over here, we're mixing the additions and the carrying. They get interwoven, and so it's important to have them sort of organized visually. That's a big advantage. And for other advantages, well, there's again the possibility of proceeding from the big end. For example, let's say we only wanted to know roughly what this number was. Okay, so then we would proceed from the big end. And once we have the 28 here and recognize that it's in the hundreds position, we could sort of replace these things with almost with question marks. And so we could, get maybe 28 and then something, something. So if we were only interested in approximating the answer instead of getting an exact answer, then perhaps this approach would be maybe a little bit conceptually simpler. Now, I'd like to finish just by talking a little bit more about the idea of using math classes to play games like Monopoly, which I think is a useful thing. And perhaps getting some input from you viewers. Have you used this kind of approach? Are there any teachers out there that let their kids play Monopoly in math class? If so, how does it work? What are the conditions that you use? How do you make it work? So anyway, here's just some of my thoughts, which are admittedly from a very external point of view. So the first suggestion might be that we could encourage each child to make their own transactions. So maybe there's a central bank in the middle with all the money that's in the bank in the middle. And when a child lands on a property and wants to buy it, well, then they have to put the $250 or whatever it is, into the bank and find the property and get the property card. While everybody is making their transactions, I think the other people can be looking and just checking whether the transactions are proceeding correctly. If somebody has to pay a fine, that they pay the right amount. If somebody is buying a piece of property and they actually put in the right amount there. So in a friendly kind of supportive way, so that everybody in the table is watching what's happening, because we want to promote the mathematical aspect, and checking that things are proceeding in a good way. It might be that if you have a really young kids, like grade 1 kids or something, maybe it would be good to have some older kids to help out. You have some older kids sitting at the tables to help out with the banking transactions, just to give them some more support. I would suggest that probably we don't want to have the games proceeding too long. Maybe half an hour or a little bit more might be all right. At the end of half an hour, we bundle all the kids' holdings in a little elastic band and put them all together, so that the next day when we start again, or whenever the next playing session is, then everybody can start from where they were, and In the meantime, they can spend a few days thinking about what they're going to do or negotiating with other people, and they can get excited by the dynamic unfolding of this game, perhaps over some days. A very important thing that we're going to have to talk more about is how to make change. So we have not talked about subtraction yet. Okay, so if a child wants to buy a property and maybe it costs $230 and they have $300 bills, they want to give $300, they want to get $70 in return. How do they figure out that it's $70 that they should get back? Well, for that, we need to teach them how to do that. And there is a method of this, making change by counting up, that I want to talk about. It's interesting because it only requires really addition skills. So it's building on the arithmetic that we have already developed and not going to the, I think, more advanced stage of actually requiring subtraction. So we'd like to be able to do this by minimizing the need for, extra mathematical knowledge. And at the end, well, whatever the end is, you define the end how you like. Maybe if they're younger kids, you might even forget about hotels and such and just play until all the properties have been bought. And then at that stage, the game is over and we count assets. So everybody has to count what their total number of assets is, the values of their properties plus their money. That's a great little exercise right along the lines of what we've been talking about. Okay, so you have some kind of clear defined end, there's a winner, and everyone is happy. So, okay, these are just some ideas. Perhaps you have other ideas or better ideas. Anyway, I think it'd be nice to have a discussion about generally, how can we make math classes for primary school kids more interesting and more fun? So I think the fun is the critical word there. And so there's probably all kinds of ways that we can think about doing that. And maybe they don't align directly with curricula, and maybe, educating bodies need to be a little bit more flexible about curricula, maybe. Okay, in any case, next time I want to talk a little bit more about this interesting, this issue here of how to make change by counting up. Okay, that's quite an interesting technique. That's a precursor to learning subtraction and actually is, traditionally very used in economics, in shops and so on. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.